So we were here yesterday. This is where we stopped. So we're going to recap a little bit. 30, 60, 90 triangles, 45, 45, 90 triangles from geometry, right? And they have a lot of importance with trig. And when we're talking about right triangles and we're looking for missing sides and angles, we have a few options. One of them is Pythagorean theorem, right? Pythagorean theorem is not going to help me with missing angles, but it's going to help me with a missing side if I know two of them in a right triangle. Special right triangles, if I know just one side and I have one of the special angles, then I can't use Pythagorean theorem because I only have one side, but I could use special right triangles. If I have one side and an angle and it's not a special angle, then I can use trig. I can also use trig on these, like in the calculator, but they would give me the same values, but they would be in decimal answers. And there are reasons we want exact values. Okay, so let's go through. We already went through yesterday. We found all the trig ratios for the 30-degree angle. We're now going to do it for the 60-degree angle in the same triangle. So I purposefully didn't write opposite, hypotenuse, and whatnot on here because we're about to change. So when we did 30, this was the opposite side, this was the adjacent side, right? But now we're doing 60, and those change. Now this is the opposite side, this is the adjacent side, right? What do you have, second period? Oh, that's why. Okay. All right. I already lost my train of thought. Oh, okay. So we're doing 60 degrees now. So when I look at 60 and I want sine, I want opposite over hypotenuse. That's going to give me square root of 3. Oops. Do it the same way here. Square root of 3 over 2. Then I'm going to go to the cosine of 60. That's adjacent over hypotenuse. That is 1/2. Right? Then I'm going to go to tangent of 60. That is opposite over adjacent. So since that's the square root of 3 over 1, it's just the square root of 3. We agree with all that? Okay. Now, how do I say this? Cosecant. So cosecant is the reciprocal of what? Sine. So since sine is the square root of 3 over 2, I want the reciprocal. Have we already found the reciprocal of the square root of 3 over 2 somewhere? Didn't we do it right here? So isn't this my answer? We don't have to redo the work. Okay. So 2 square roots of 3 over 3. How do I say this? Secant. And secant is the reciprocal of cosine. So what is my answer here? 2. How do I say this? Cotangent. Cotangent is the reciprocal of tangent. What's the reciprocal of the square root of 3? Square root of 3 over 3. What's the reciprocal of the square root of a monkey? Square root of a monkey over a monkey, right? Doesn't matter what it is. All right, everybody good on those? Now I want you to look at all the numbers that we have. Oh, I forgot to mark this one out just because I don't want to look at it. It's not wrong or anything. And look at them for a minute and tell me what you notice. They're both what? Oh, I'm sorry. What you notice about the purple numbers we wrote. Yes, you're right about the angles up here. Sorry. Let me clarify my question. The purple numbers we wrote in the chart, look at those numbers. And tell me what you notice. We have all the same values in there, right? They're just in different spots. What can you tell me about the sine of theta? What is it? I'm sorry, obviously sine of theta. The sine of 30 is the same as what? Cosine of 60. And the cosine of 30 is the same as sine of 60, right? That should make sense to you because they're both over hypotenuse, right? But one of them's opposite, one of them's adjacent, and when we switched angles, they just switched places, yes? And since opposite and adjacent switched, that's what makes the tangent and the cotangent switch places here. So there's a lot of reasons that I want you to notice these patterns right now, but one of them is that eventually, at the end of next week some point, I'm going to expect you to be able to tell me what's the cosine of 30, what's the sine of 60, those things very, very quickly. I do not expect that right now. Right now we are coming up with it from the triangles. This is not a matter of memorization. We're going to do a lot of things where I'm going to baby step you through the learning process. And if you stick with me and listen and actually do it and not panic, then you will get there slowly. It's a slow process, but I'm going to give you a ton of tools. We're going to look at a ton of different patterns, and different people's brains work different ways, and you're going to latch onto one thing where somebody else is going to latch onto something else, and it's going to make sense to both of you, and that's totally fine. But I have a ton of tools in my toolbox to share with you. So if one thing isn't working and I'm like, just hang on, I'm going to give you something else, or it's going to take a little while. That's why I said like it takes some marinating. But again, it's not memorization. You can, but that's really not the best. Understanding the relationships is the best way, so that even if we don't talk about it for a while, like you can come back and go, okay, I know how to figure that out. Worst case scenario, or like worst case scenarios, you can figure it out from special right triangles, but we definitely don't want to have to do this every time we need them, right? We're not going through all this. I'm just showing you where it comes from, all right? Now, Jesse, tell me what you notice about the second triangle. What'd you tell me a minute ago when I asked the other question? I'm sorry, I call you Jesse all the time. Philip, good, I know the difference. See, I don't know, guys. Philip, sir. There you go, 2 45s. All right, so I have 2 45-degree angles, right? That's why these are the same. We already said that yesterday. What kind of triangle is this? It is a right triangle. What else? We've got 2 congruent sides. That makes it what? Did any of you take geometry? What? Isosceles, yes. It is an isosceles right triangle. Isosceles, ooh, yeah, there we go. Isosceles right triangle. Isosceles triangles have at least 2 congruent sides, right? So a little fun fact. Is this an isosceles triangle? That's not my question. It's a yes or no question. Is this an isosceles triangle? Yes. A better name is equilateral, but it is isosceles because the definition of an isosceles triangle is not 2 congruent sides. It's at least 2 congruent sides. So little... Yeah, a square is a rectangle. It's just the better name is a square. Yes, absolutely. Absolutely. All right, so now let's set these up for 45. So sine of 45 degrees. Now, I've got 2 45-degree angles. Does it matter which one I pick? No. So let's just pick this bottom one because that's what we picked over there. So if I want to do sine, that is opposite over hypotenuse. So that's 1 over the square root of 2. That's basically the reciprocal of the square root of 2, which is what? Square root of 2 over 2, right. And then I'm going to mark it out just so we're not looking at it, but I don't expect you to jump to that just yet, if, some of you maybe, but. All right, so then cosine of theta. Cosine of 45, adjacent over hypotenuse. Well, guess what? That's 1 over the square root of 2 again, which is the square root of 2 over 2. So hopefully it makes sense that those two are the same since opposite and adjacent are the same, right? All right, so then tangent of theta. I've got 1 over 1. What's that? 1. All right, so then cosecant is the reciprocal of sine. So what's the value here? Square root of 2. Very good. So then what's the secant value? Square root of 2. Cotangent's the reciprocal of tangent. What's the reciprocal of 1? 1. Thank you. Y'all remember the last time I asked that exact same question, and in 3 of my 4 classes, I got the answer of 0, which is not right. It's like a knife through my heart. Okay, so now just look at my orange numbers. Yes, they're different than the purple numbers. It should make sense that they're different, but we kind of wrote the same thing over and over again, right? So there's not a whole lot of a whole lot of numbers to actually know. So when I ask you these questions, the sine of 30, and for right now, remember, we're only going to be working with sine, cosine, and tangent for a long time before we really start to worry about what these values over here are. And so if you look at that, you just have a finite number of answers. There's actually just 3 different things you can say. 4. Your answer is either 1/2, square root of 3 over 2, square root of 3 over 3, square root of 2 over 2, or 1. Those are the only things you have to choose from, right? We just got to put them in the right spots. So although this chart, I'm sure, looks very overwhelming, in the end, it's not going to be. Again, if you can just trust me and let me step you through it slowly. All right? Are we all good? Great. Okay, so we are going to get this stuff put in our ISN before we continue on. All right, so the calendar said 70. This is actually 71 since we just fixed all that stuff. And we're going to look at angle measures. All right, so you've done lots of things with angles in your math career. I'm not sure how much you have actually done, if any, with angles in the coordinate plane. All right, so you can have an angle in a triangle, you can have an angle wherever, just, two parallel lines cut by a transversal and have angles, but we can also graph them in the coordinate plane. You can graph them anywhere in the coordinate plane, but all we're really concerned with right now is in standard position. This says standard form over and over again, which is the same thing, but standard position to me makes more sense. So this says an angle in the coordinate plane, which means your XY plane that you are already so familiar with. In standard form or standard position, when the vertex is on the origin and one ray lies on the positive x-axis. So when you look at this little thing over here, there's the origin, that's the vertex of the angle, and one ray is on the positive x-axis. Okay? The ray on the x-axis that I just drew is called the initial side. Because that's where we start. So I tried, maybe I'll do it this way. Okay, there we go. That might work. Oh, that works better. Okay, so we're starting here. Like, this is the x-axis, right? This is my ray. We're starting here. My degrees of my angle are 0, right? So the other ray over here, the other side of the angle, that is called the terminal side. Ready? So I start here like this. I rotate like this, which makes this my initial ray or my initial side and this my terminal side. Now, by looking at questions in AP Classroom, that vocabulary is very important because I saw some questions where there wasn't a picture for you and it said the initial side is blah, 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 and the terminal side, blah, blah, blah. And so if you don't know what those are, it makes it very complicated. If you do know what it is, it makes it very easy because you can sketch a picture real quick and it's no big deal. All right, so make sure you know the differences there. All right, so when we start here at 0, we can either go counterclockwise or clockwise, okay? You have to know how a clock goes for that to make sense. And not a digital clock, but this one up here. Watch the second hand for a minute. The way in which it is rotating is what is called clockwise. We good? We all know. Even if you can't read a clock, do you at least know which way the hands go? That's what's important right now. Okay, so we're here. And I'm here at 0. If I go counterclockwise like this, because it's opposite of what the clock would do, right? That results in positive angle measures. Right? If I go clockwise like the clock does, and I go this way from 0, that results in negative angle measures. So if you did not know, if you did not know that negative angles exist, that kind of looks like a negative. It looks funky. That's an N, negative. If you did not know that negative angles exist, they absolutely do. Having a negative angle inside of a triangle, does that make any sense? No, it does not. In the coordinate plane, yes, it does. Okay, we all good with that? And that's why we have this little arrow here showing the direction of the rotation, and that angle there is theta. Everybody okay with that so far? Good deal. All right. So the most common unit of measure for angles is the degree. It's the only one you knew existed until you got to geometry, most likely. Okay, and you've known degrees for a long time. There's a little degree symbol over there. So how many degrees are in a circle? 360. So if I go all the way around, that's 360 degrees. If I go 1 degree, that is equivalent to 1/360th of a full rotation. Does that make sense to you? Yes? Okay. All right, so because of the way that we rotate in the coordinate plane, that is why the quadrants are numbered the way they are, if you ever wondered. Because when I start here at 0 and I rotate to 90 and then 180 and then 270 and then 360, I rotate through the first quadrant first, This is the second quadrant I rotate through. This is the third quadrant I rotate through. And this is the fourth quadrant that I rotate through. Okay? You have to know which quadrant is which. That is definitely not new information. Okay? All right, so now we are going to sketch an angle in standard form with the given measure. So I'm going to sketch a 135 degree angle. So I start with this right here, right? I start on the positive x-axis, that's one ray. Then I'm going to rotate. Well, I know when I go from here to here, that's 90. And if I went all the way to here, that's 180. So somewhere in the second quadrant is 135. I kind of need to know exactly where. So if I subtract 90, what's 135 minus 90? 45. 45 is how far through the second quadrant? Halfway. Now, we're not getting out protractors, and we don't have to be exact, but, and don't draw this because it's wrong, if you do this and try and tell me it's 135, I'm not taking that mess because you didn't even try or think about what the values were. Make sense? You need to make an honest effort. So, that means that I'm going to aim for halfway, make it look like that. Okay? We good with that? What questions you got? Because I needed to know how much farther than 90 to go. Because I know if I go from here to here, that's 90. And then from here to here, it's 180. So I know it's in here somewhere. So if I subtract 90, I figure out how much more I have to do. So I knew that it was halfway through that second quadrant. Yes? We're getting there. Okay. Let's look at number 2 real quick. 495 degrees. So I'm going to start here. Now, and you may not even have known that those kind of degrees exist, but they do. Angle in a triangle doesn't make any sense. Angle in a coordinate plane absolutely makes sense. So if I'm here and I rotate 90, 180, 270, 360, well, and then I know if I go another 360, that's 720. So I have to go one rotation and a little bit more. So I'm going to subtract 360 to figure out how much farther to go. What is 495 minus 360? 135. And that was what we had for number 1, right? So I'm going to draw that. Now, if I look at these two pictures, they look identical, don't they? Do they represent the exact same angle? No, they do not. So doing this is not enough, which is answering your question right there. You have to show not only the direction of rotation, because I also don't know if maybe it could have been a negative angle. There's a lot of ways. There's an infinite amount of ways to land right there, right? And so for this 135, I need to do this, and I can say this is 135 degrees. For this one, I'm here. I rotate all the way around and then a little bit more, and this is 495 degrees. So even if I didn't write the numbers, do you see how the arrows tell you that they're different? Yes? We good with that? Okay. Number 3, I have a negative 140 degrees. So I'm going to start right here. Which way am I going to rotate? Clockwise. So if I go clockwise, if I go from here to here, that's a negative 90. This would be a negative 180. So I'm somewhere in, what quadrant is this? Third. So 140, and this is 90. How much farther do I have to go? 50. And 50 and 45 are pretty darn close, so I'm okay with that. But then again, I need to show that that was a negative rotation. That's a negative 140 degrees. Okay. What questions do you have? Anything? Okay, good deal. All right, so now let's talk about radians, okay? Because radians is another unit of measure that you were introduced to in geometry. Now, it is very likely that you were introduced and didn't do a whole lot with it because there's not a whole lot that's expected except an introduction and tying it to arc length. But depending on who your teacher was, you might have, why does that arrow do that sometimes? See, look at, where was that supposed to be? Right there? Oh, I don't know why the arrow stays. These boards, I tell you what. Let me see if I can turn the page and come back, and maybe it'll stay put now. There we go. I don't have any idea why that stuff happens. Okay, so let's talk radians. A radian is a unit of angle measure. So just like you can measure distance in inches and centimeters, and they're different, radians and degrees are different. They're also a different type of measure, but still there are different ways to talk about angles. A unit of angle measure based on arc length. So 1 radian is defined as the measure of the angle formed when the radius is equivalent to the length of the intercepted arc. And I'm going to show you a really quick, like 1 minute video. No, I'm sorry, not 1 minute, like 10 seconds. And then we're going to talk about that. So let's see, let's get this. Hopefully my speaker stayed on.
We start with a circle of radius r. We take that radius distance and wrap it around the circle. The angle formed by that radius distance is 1 radian. Since the circumference of a circle is 2 pi r, there should be 2 pi radiuses in a circle. So halfway around the circle, we would expect 1 pi radian. And around the entire circle, we would expect 2 pi radians.
There you go. That's your definition of a radian. So I'm going to take you through this again a little bit. So we have a circle. The radius is whatever it is. It's r. That length is what gets wrapped around this circle. Boom, right there. Okay. So this is a certain number of degrees. It's somewhere in the 50s. I don't know what it is exactly. You don't need to know what it is exactly because it doesn't really matter. But it is the length of whatever this radius is. Okay? If this radius is 1, this has a length of 1. Right? If this radius is 6, it has a length of 6. But then the amount of radians comes from the ratio of the two. So that is 1 radian. And we know that the circumference of a circle is 2 pi r. So if the radian is the length of the radius, what he was saying, then we have 2 pi radians. So from 0 to 180 would be pi radians, and then all the way to 360 is 2 pi radians. Okay? That makes sense? Okay, so just a different way to look at it. So we know that 360 is equal to 2 pi radians, like we just said, and 180 is equal to pi radians. All right. Now, we're going to talk about converting, and that's basically what this little picture over here shows, too, is that you have, this is the radius, and when you wrap it around, you get a radian, and this is your theta. Theta is equal to 1 radian in that case, okay? But we need to be able to convert between the two. We're going to talk about how to convert. We're going to convert a little bit, but really when we get down to all this, we're not converting a whole bunch all the time. We're going to look at things a little bit of a different way, but this way at least kind of shows you the relationship. So because we can set up a proportion and say I have whatever degrees over 180 equals the number of radians over pi and then multiply, that's where you come up with these little equations here. If I want radians and I have degrees, that means I need to get the pi in my answer, so it's going to be pi over 180. If I want degrees and I have radians, I got to get the pi out of it, so I got to divide by pi and 180 is on the top. So it's either pi over 180 or 180 over pi. And it's kind of hard to get it wrong, because if you get it wrong, it doesn't make any sense, because you'll end up with like pi squared or no pi's or something like that, okay? All right, so let's look at how to convert these. And it says to state which quadrants. So let's look at our quadrants. So 60 degrees, which quadrant is that in? The first. Okay, so we are in quadrant 1. And then we're going to convert. So we're going to take 60, that's degrees, so I'm going to multiply it by pi over 180. So I'm going to simplify before I actually multiply. The zeros will cancel out. Then how many times does 6 go into 18? 3. So is my answer 3 pi? No, it is pi over 3. Pi thirds. And it's not 1/3 pi, it's pi thirds. Everything with these radians, it's always all in one fraction. Okay? All right, so then 160. What quadrant would that be in? 2, because we're not quite to 180 yet, right? So we're in quadrant 2. So then I'm going to take 160, and I'm going to multiply it by pi over 180. Once again, the zeros cancel out. Let's see, 16 and 18 are both divisible by 2, so I'll divide them both by 2. In the numerator, I will get 8 pi. In the denominator, I get 9. Can I reduce that anymore? No. And notice it's 8 pi over 9. It is not 8/9 pi. Everybody okay with that? All right, negative 330. Now this is negative. Is it going to make what we do any more difficult? No. What quadrant do you think that is in? First, good, because I would start here. Since it's negative, I rotate this way, and I'm not quite to 360. I'm there at 330, so, or negative 330, and that's in quadrant 1. All right, so then we're going to have negative 330 times pi over 180. Once again, I can cancel those zeros out. I know my answer is negative. What are 33 and 18 both divisible by? 3. So this is going to give me negative 11 pi over 6. Can I reduce that anymore? Nope, that's my answer. What questions you got? We good? Now, I'm going to challenge you a little bit. I'm going to challenge your brains. And we are going to state the quadrant of these radian measures before we convert. Now, I am well aware of the fact that you are not experts at radians. I don't expect you to just be able to stop this out very quickly. But I want you to be able to think critically around the circle. Listen to the way I'm having you think. Listen to the things I'm saying. And this is the way we need to be thinking around the circle that will help you from here on out. And why can't I scroll? Okay. So I want you to look at, we're going to do a little X and Y axis down here. You have a little bit of room, right? Or off to the side somewhere. It doesn't have to be big, but put it somewhere. All right, so I know if I start here, I'm at 0. If I go all the way around, that's 360 degrees, which is how many radians? 2 what? Pi. So it's 2 pi radians. So 180 is what? Pi radians. So what do you think 90 is? Half of this, so that would be pi over 2. Now, here's what we're going to think about before we get to this one here. Every 90 degrees of a rotation, I'm going pi halves radians. You agree with that? So we're going to think fractionally through all that. And with me using the word fraction, don't let that freak you out and your brain shut down, okay? Thinking fractionally is not that big a deal as long as you're awake, Adam. So I've got 0. This is, okay, so this is pi halves, right? If I go another 90, this is 2 pi halves, yes? And 2 pi halves, the 2's cancel out. That's why I end up with pi when I reduce it. You with me on that? So how many pi halves is this? 3. So this is 3 pi halves. And then this is 4 pi halves, which reduces to 2 pi. Does that make sense? So we're thinking fractionally, no matter what the fraction might be. So when we start with number 7 here, with 5 pi 18ths, whatever your denominator is, that's the fractions we're thinking about. So if I'm here at 0, then when I get to pi, if I'm thinking in terms of 18ths, wouldn't this be 18 pi over 18? You with me on that? Isn't that the same thing? If I had 18 pi over 18, I wouldn't actually write it like that because they would cancel out and give me pi, right? But if I'm trying to think fractionally, this is 18 pi over 18. We agree with that? So then in terms of 18ths, what would this be? 9 pi over 18, right? Because that would reduce to 1/2. So this is 9 pi over 18. Understanding that much, tell me what quadrant is 5 pi over 18 in? 1, because it has to be somewhere between 0 pi 18ths and 9 pi 18ths, right? So just that thought around the circle there, we have to be in quadrant 1. Now here's the thing. We're about to convert, and if we're wrong, we can fix it. Because it's okay if we don't 100% grasp this right now. On your assignment with these kinds of questions, I want you to, before you convert, try and think around the circle about what quadrant it would be in, and then if you're wrong, fix it. It's fine. But this will get much, much easier. So don't freak out if it's not totally making sense just yet, okay? Because I am challenging you a little bit here. So now let's convert and see what happens. I have 5 pi over 18. I am going to convert that to degrees, which means I need to divide the pi out. So this one's going to be 180 over pi, right? So then the pi's cancel out. How many times does 18 go into 180? 10. So this becomes 10. So I just end up with 5 times 10, which is 50 degrees. And I do believe that is in the first quadrant. Everybody okay with that? What questions do you have? What's your question? Are you sure? Okay, it's okay. It'll get better. By number 9, I think hopefully it'll make a little bit more sense, all right? So we've got negative 11 pi over 9. So we're going to think fractionally, but this time in terms of ninths, okay? I'm here at 0. Would also help if you made sense, if you paid attention. All right, so I'm here at 0. If I go to negative pi, I need a value of 1, so this would be 9 pi ninths. Do you agree with that? Okay, so this would be 9 pi ninths. This would be 18 pi ninths, yes? So 0, 9 pi ninths, 18 pi ninths would give me 2 pi. So 11 pi ninths is just a little past that. We're going to be in this quadrant, which one is that? Which quadrant is that? Second. Okay, I thought I heard sixth, and that worried me a little bit, but okay. I guess you said second. It's like sixth. I don't know about that. All right, so negative 11 pi ninths. And this, I probably should have changed this one because it's hard to do the halves there, I know. We're going to multiply that by 180 over pi. So now the pi's cancel out. I know this is negative. How many times does 9 go into 180? 20. So then I have 11 times 20. What's that? Negative 220. And I think that would mean I would go from here to negative 180 and then another 40. I believe I'm correct about the second quadrant. Okay, we okay with that? Degrees, yeah. Negative 220 degrees. All right, so let's look at 7 pi thirds. I start here at 0. When I get to pi, what do I think about in thirds? What would this be? 3 pi thirds, right? Okay, does everybody understand why that's 3 pi thirds? Because that obviously we wouldn't write it like that, we'd write pi, but we're thinking fractionally. So 3 pi thirds. If I go all the way to here, how many pi thirds is that? 6 pi thirds, right? So 0, 3 pi thirds, 6 pi thirds, 9 pi thirds, 12 pi, like I could keep going, but 3 pi thirds, 6 pi thirds. Well, I need 7 pi thirds. If I go a third of the way from here to here, what quadrant am I in? First. Okay. So then I'm going to do 7 pi thirds, and I'm going to multiply that by 180 over pi. These pi's are going to cancel out. How many times does 3 go into 180? 60. And 7 times 60 would give me 420 degrees. Okay, so I'd go 360 and another 60. That would put me in the first quadrant. Now, normally, listen, shh. Normally I do this lesson where we do the entire thing all in one day, but it kind of didn't work that way because I didn't finish and we've been talking about some other things. And we do a lot more of this type of thinking on the back. All right, which helps you make it a little bit more sense. I don't want you freaking out if you didn't understand the whole quadrant thing 100% right now, okay? But after we finish the back, you'll get much, much more comfortable with it, I promise, okay? You got to trust me.